Hey guys, back again. Ready for another wonderful lesson in AP Statistics. A couple things new today. I'm trying to get all my notes out to you so I'm not writing them out so much. These are some things that we definitely need to think about as we move forward to section 9.3. That's about population means, not means. Okay. Remember in this video, I'm using material that has been um, posted for you in Google Classroom. When you see this video, it's there, so you can print out all the things that I've got. So a couple things we want to do. We definitely want to remember that population means involve mu. We are no longer dealing with p. P is for proportions. Mu is for means. So the population parameter that we're dealing with is mu. We are also dealing with x bar and not p for a sample, or p hat for a sample proportion. Okay. The hypothesis tests have the same format: the state, plan, do, and conclude. So we have done a couple, so we should be able to kind of just take that format and run with it. We're either going to have a one-tailed or a two-tailed test, and it's going to be a t-test. Up at the top there it says sigma unknown, and I made the point before we left face-to-face education that sigma is very rarely known. You would never know your population standard deviation without knowing your population mean. So sigma unknown is the way the book that you have deals with this problem. So it is a t-test, just like the t-statistic you used for a confidence interval. It is a t-test. It's two-tailed if it's not equal to, and we're talking about the null hypothesis. And if it's less than or greater than, then it's a one-tailed test. You must use the t-distribution in table B to find the p-value, or you can use your calculator, and you must find the degrees of freedom. Degrees of freedom are always going to be your sample size minus 1. If you've been watching the videos that AP has put out about the chi-squared test, they have a different way of figuring out degrees of freedom. And man, I wish I was here in person with you giving the chi-square lessons, because I'm learning things too. And something that kind of shot a thunderbolt through me is how they explained what degrees of freedom for a two-way table was. It was like, whoa, that's awesome. So anyway, just an aside there. Conditions, random, independence, and normality. Same exact ones that we're dealing with for the other test. We deal with normality this time, just like we did with the confidence interval. It's either going to be stated that the population is a normally distributed population, and that's great because that's a little less work than anything else. We could have a large sample size, which means n is equal to 30 or more, then that's the central limit theorem. Or we could have a graphic representation. So some things you're going to have to put as a graph, some things you're going to have to talk about as a large sample size. And then I gave you some sentence frames. I know on the last graded homework that I've done, there was an issue with people stating their conclusions. And I want to make sure that we understand these are pretty much the conclusions that I think you should come with. Assuming the null hypothesis is true, there is a blank probability of getting a test statistic, whether it's t, whether it's z, of whatever that value is, or greater or less than, depending on which way we're going, if we're going left or right, or by chance alone. Okay, so that's the first thing. And then our decision to reject or fail to reject is number 2, because our p-value of whatever is less than alpha, and whatever that alpha value is, we reject the null hypothesis. So the p-value is less than, we reject. Or the p-value is greater than the alpha value, we fail to reject. And that's really it. There's no other decision like, we support, we do, that, we find evidence this way. No, it's reject or fail to reject. And then the third part, putting in your conclusion in context. We have convincing evidence to support the alternative hypothesis in context, or we do not have convincing evidence to support the alternative hypothesis in context. Okay, and that's it. That's what the things we should be dealing with for a population mean, one population mean test. Okay. All right, so let's get going. First one, Ernesto. He's made his triumphant return. I'm not going to mention where he's from. I think he's moved. Anyway, Ernesto claims that the onions he grows have a mean weight of 1.2 pounds. Those are some big onions. If a simple random sample of 35 onions has a sample standard deviation of 0.6 pounds and a sample mean of 1 pound, investigate the claim that the mean weight of Ernesto's onions is less than 1.2 pounds at an alpha of 4%. Assume all the conditions are satisfied. Okay, so we don't have to do the conditions on this. I'm going to address them as I go through the video, but we're not going to full on write out the conditions. Okay, you guys have done that enough. The conditions, go back and look at the other information that we have. Of course, the page that I'm looking at on my green sheet, on the Pepsi sheet, is the test for a population mean sigma unknown. So there's the null hypothesis. There's your test statistic sitting right there. Remember, the test statistic is T, and we're dealing with our data point that we got from our sample, so our X, okay, in this case, and then minus our population parameter, what we're assuming that mu is, divided by our standard deviation. Well, our standard deviation, because our sample size isn't 1, we have to do S divided by the square root of n. And then our degrees of freedom is our sample size minus 1. There's our conditions, some random sample, normality, which I talked about, stated large sample size or graphic representation, and then independence. All these, the observations are going to be independent. Or excuse me, the observations are not going to be independent for the most part, which means we're going to have to do the 10% rule or the 10% condition. Okay, so let's get going. Okay, so Ernesto claims that the onion seed grows has a mean weight of 1.2 pounds. Mu is right there. A simple random sample of 35 onions, there's your N. Sample standard deviation, there's your S. And a sample mean of 1, that's your X bar. Investigate the claim that the mean weight of Ernesto's onions is less than 1.2 pounds. Okay, so our null hypothesis would be, again, we are not dealing with a sample, we're dealing with a population. We're saying that the population of Ernesto's onions has a mean weight of 1.2 pounds. An alternative hypothesis, well, the sample mean was down to 1 pound. So we have some evidence, not convincing, we have to figure out if it's convincing or not, but we have some evidence that maybe the mean is really less than 1.2 pounds because we've got a sample statistic that says so. Okay, so our alternate hypothesis mu is less than 1.2, and we have to tell what mu is. We can do that in the state or in the plan. Our alpha value is at 0.04. Okay, so sometimes it's 0.05, sometimes it's 0.01. Sometimes when Mr. Kimley gets silly, he just changes it willy-nilly. Okay, it's at 4% this time. So now there's the state. Now here's the plan. We will perform a, let's name it. This is a one population. One-tailed t-test for mu, which equals the true population mean weight of Ernesto's onions. So we named the test. It's a one-tailed t-test. It's for one population. We've named the population of interest. The population of interest is the mean weight of Ernesto's onions, and that's what our variable mu stands for. If we're going to use a variable in our hypothesis, we have to name it. Okay. So now we would go on to our conditions. Sorry, let's go with random. And I'm going to not do the full one here. I'm just going to basically do a check off in the interest of saving some time since we already know how to do this. Was it a simple random sample? If a simple random sample of 35 onions, yes, we have a simple random sample, which means we'll be able to generalize to the entire population of Ernesto's onions. Next, independence. Okay, is the independence of sampling there? In other words, did we pick an onion out of the pack for when we sampled it and weigh it and then throw it back in so it could be possibly picked again? That's sampling with replacement. We don't have that here. So we have to check the 10% rule. This is for sampling without replacement. Okay? And so that basically says, is n greater than 10 times little n? Well, the sample size is 35. Do we think that Ernesto, who is a farmer, raises less than 350 onions? I think it's a pretty safe bet that he grows more than 350 onions. So we're going to say that that is check mark. We have to do an assumption there. Now, normality. It never said that the population of onions was normally distributed weight-wise. Okay? So that doesn't work. That's the first one it's stated. The next thing we would want to look at is large sample size. Dun, dun, dun. We have sample size of 35. That's more than 30. So normality is yes. The sampling distribution of the sampling mean is approximately normal because the sample size is greater than 30. And then you can make a mention that that, of course, is because of the central limit there. Now, if we had data, and you're going to have data on the problem that you're going to have to do for homework. I'm going to quickly go to that real quick. We have data there. You're going to have to figure out the sample mean. You're going to have to figure out the sample standard deviation, which is easy to do when you have a calculator do it for you. Remember, get the sample standard deviation, not the population standard deviation, the sample standard deviation for this problem. And then that doesn't say anywhere in there, and since there's only 20 data points, you are going to have to do a graph. Now, what could you do for a graph? Could you do a dot plot? Yes, you could. Could you do the normal probability plot? Yes, you could. Any way to show that this data does not have outliers and does not have strong skewness. Let me say that again, and I'll put this up here. No strong skewness
Good evening, Upland Unified students, parents, and staff. This is your superintendent of schools, Dr. Kelly. In coordination with public health agencies, the governor's office, and schools across the region and state, the Upland Unified School.
Okay, sorry about that. I don't know what the videos exactly picked up there. That was an all call from our superintendent, so I wanted to listen to it in real time, and now I'm back to the video. I'm sure that the news from that will not make you a whole lot of happy. We just need to kind of push on and do the best we can for this class and for the AP test that's coming up. I'm going to do my absolute dead level best the rest of this video to kind of compartmentalize, and then we'll figure this out together. Okay, so back to the problem. No strong skewness and no outliers. Okay, so that means, of course, there could be a little skewness, but no strong skewness. Okay, and then there's no outliers. If you find those, then basically you've not um, you're not able to pass the conditions, and the what we are doing, the processes that we're doing, it really shouldn't even be followed. So the point of doing the test is kind of over. So and what you do in case of those things is kind of beyond this course. This is entry level, so we're looking at everything like everything kind of works out the way it's supposed to. So anyway, that's on the second problem. So that's just a little bit of the homework problem. That's just a little bit of heads up for that. Okay, let's get back to our real problem. We've passed all the conditions, and that's what we would do. Of course, I've got check marks there. That's certainly not what you do. You write it out, and you make a reasonable attempt at explaining your thinking there. Okay. Now, to find the test statistic, I always draw the situation. You know that. Okay. Our mean, of course, is 1.2. Our standard deviation is 0.6. So oh, sorry, no, it's not. The standard deviation for the sample was 0.6. We have to do the standard deviation, so that's not necessarily the case. So let's go through here and figure some things out before I do that. Okay, the mu we're looking at is 1.2. The the um, the sampling standard deviation, or is it the sampling mean? I'm just losing my mind. Sorry. We got was 1. The sample standard deviation was 0.6. Okay. Now, if we're going to talk about um, the standard deviation of our sampling distribution, we have to take that into effect because that's what the t-statistic gives us. So S divided by root n is going to be 0.6 divided by the square root of the sample size, the square root of 35. 35, not 36, you knucklehead. So it's going to be about 0.1. 0.101. So we're going to make it 0.1. So then this will be 1.1 and 1.0 about for 1 standard deviation, 2 standard deviations. And there we are. That makes a lot more sense to my immediately over-calculating brain that goes, wait a minute, there's a problem with it. Okay. So we are looking to figure out where our sample ended up being. Where our sample ended up being right here at 1. And that's almost 2 standard deviations away from the mean. And so that's in the area where we would probably think that we're going to have some issues. Okay. Anyway, let's do our t-statistic. Again, that is x bar minus mu over s divided by the square root of n. So x bar is 1 minus mu, which is 1.2, divided by this 0.101 number. I've got it in my calculator still, so I'm going to divide by the entire number. So it's this will be negative 1.97. That's our t-statistic. Okay, so t equals negative 1.97. And our degrees of freedom, remember n is 35. That was the number we put in there. So degrees of freedom will be 35 minus 1, or 34. So let's look it up on our sheet, figure out where we're at. Make sure you're looking at the t-distribution. It's table B. And the degrees of freedom goes all the way down to 20. You flip the page, and now it goes all the way to 30, but then it skips to 40. So 34 is kind of halfway in between there. We use the most conservative value, so we're going to use the 30. Okay? So the degrees of freedom of 30, and now we have the tail probability that we have to figure out for our statistic of negative 1.97. Remember, this is the upper tail. We're actually looking at a lower tail. So this area here for a t-statistic is going to be in this tail down here, but it's the same as this one up here. So even though we're looking at a negative, really it's when we look this up on the table, it's going to be the same as the area in the upper tail would have been. Okay, so now 1.97 degrees of freedom of 30. We go over here until we find 1.97. All right. So, our 1.97 is right in the middle there. 1.697 and 2.042. Huh. That's good. So now we know, I'm going to go up there, and now we know that our tail probability is going to be between 0.05 and 0.025. Ouch. That's right in between. So our 1.97 is right in between those two numbers. 2.042 and 1.697. Okay? So that means the tail probability, our p-value, is going to be between, and the things switched here. The 2.042 is a tail probability of 0.025, and the 1.697 is a tail probability of 0.05. Okay, so these switched. Okay, and as they always do. So now we don't know where our p-value is other than between these 2 points. So if I was to do a decision on this, my alpha value is at 4%. If my p-value is somewhere between these two, and my alpha value is 0.04%, I don't know if p is either greater than or less than 0.04. If this was, a p-value was less than like 0.03 here instead of 0.05, then I would know that p was completely less than 0.04, and I'd fail to reject. Excuse me, I'd reject. Duh. If this 0.025 was actually 0.04, and p was between 0.04 and 0.05, then I would know that my p-value was greater than alpha, and I'd fail to reject. So right now, if I had to make a decision based on what I have right in front of me, I could not reject it. I'd have to go to the more conservative, fail to reject. There's not enough evidence. There's not convincing evidence to support the null hypothesis that the mean weight of the onions is less than 1.2. The good news is I've got technology. So instead of finding that value from the table, okay, I'm going to find the value with technology. Okay, I suggest that you do all the stuff by hand, and then you go back and figure it out. You go back and figure it out with technology. So let's take a look at that real quick. I'm sorry I don't have some fancy thing that will put the stuff on the screen. I've seen the videos on the AP. One of the teachers has the calculator that pushes on the screen, and it's really slick. So, but we'll invest maybe. We'll figure out how to do that. Anyway, we're going to go to stat. We're going to run a test. This is going to be a 1 proportion t-test. No, because it's not a proportion. It's just a plain old t-test. Okay? Now I'm going to put in stats. I'm not going to put in data. Sometimes it asks you for your data, sometimes it doesn't. I'm going to put in my stats. So what is my hypothetical mean is 1.2. My X bar, got that as well, that's 1. My sample standard deviation is 0.6. My sample size is 35. And I am running mu less than 1.2. So I'm running a less than, or a one-sided t-test. So that is what I want right there. Not the not equal, but the less than. Okay? And I'm going to go and calculate. So my t-value is negative 1.97. Cool. That's kind of what I got by hand. And my p-value, cool. It shows me the p-value of 0.028. So now, by technology, I've got p equaling 0.028. It was just barely more than the 0.025 that I had. And now I can clearly state my conclusion because I know exactly what my alpha value is, and I know that p-value is less than that. All right, so now I can make my conclusion. So before, when I did it with the table, I was not able to make a decision. But on this, I was able to make a decision. So now I can go ahead and do that. So, by the way, I'm throwing a lot at you because I'm throwing what I would show if we were in person. I would do this over 2 days, and I would show you the problem that occurs because of this range of p-values. Introducing this range of p-values and then also showing that the problem that exists with the p-values, I apologize. We're kind of short on video time. I don't want to make you watch 3 or 4 hours worth of video for every week that we have for education. Anyway, so we've got our sentence frames. I'll find my sentence frames and I'll go along with them. Remember, the sentence frames are these 1, 2, and 3. Now our conclusion is going to be that. Okay? Assuming the null hypothesis of mu equaling 1.2 is true. I like to put the context in whenever I can. I just feel like it needs to be there. Assuming the null hypothesis of mu equaling equals 1.2 is true, there is what's the p-value? The p-value is 0.028. There is a 0.028 probability of getting a t-value I'm going to change that. Not test detectors. Getting a sample mean of, what was the sample mean on this? Of 1, and it was in pounds or less, because it was a left-tailed t-test. I think I put on there on the information that I gave you that was a test statistic. I don't mean that. I mean a sample statistic. So please change this to sample statistic. I will change it before I send it out to you guys. Or less by chance alone. In the next sentence, because our p-value, or our probability, same thing, of 0.028 is less than the alpha equals 0.04 value, we reject the null hypothesis. There's a school of thought that says once you've talked about what your null hypothesis is, once you've said it, that what your null hypothesis is, you don't have to keep writing what the null hypothesis value is and what it is. I'm not in that camp. I would rather have context the entire time. So we reject the null hypothesis. And then the last thing, we have, remember the reject was the first sentence of number 2, so we should go with the first section of number 3. We have convincing evidence to support the alternative hypothesis. Sometimes you don't need to name the alternative hypothesis. You can just put it in context. To support the alternative hypothesis that the true population mean weight of Ernesto's onions is less than 1.2 pounds. Holy cow. Okay. I can use all day going on these hypothesis tests. They take forever. Me talking through the logic behind it and going through that, that's what keeps it long. I don't think that we'll be doing a full hypothesis test, but I think there's pieces of the hypothesis test that they will pick out, and you don't have any idea what part they're going to pick out. So I'm talking about on the test. So be really good at everything and understand the logic of everything. And now you've pretty much, if you understand that, you get through the homework question that talks about putting the graph in. You've pretty much nailed 9.3. Now there's a concept called power. I'll go on to that real quick. There's a concept called power that you need to read about. It has something to do with your type 2 error. So remember in 9.1 we talked about a type 1 error and a type 2 error. The type 1 error had something to do with our alpha value, okay? And read about what power is, okay? Yeah, so really important to do that. I could understand them asking a question about power because you really have to understand everything about sample means and how to do a hypothesis test with sample means to kind of get the idea of power, okay? And it's a really easy concept once you kind of get your mind around it. So read through the section, and I will try to put something together. I honestly think this is the last video for this week. I might throw a little quiz at you for Thursday to be done by Friday, but I don't think we'll be doing another lesson. So I will show the key for the homework once you guys turn it in, and you guys can check it and make sure that you're doing the right thing. Okay. So more to follow. Yeah. Have a great day, and know that I'm working really hard for you, and trying my Algebra 2 classes obviously too. Know that I'm working hard for you, and I miss you guys all. And yeah. That's it for this video. More to follow, as always. Thanks.